Kirchhoff's second law, or the loop rule, is used to predict the potential difference or voltage at the terminals of the components of an electrical circuit. This law states that in a loop, the potential difference at the terminals of the power source is equal to the sum of the potential differences at the terminals of the other components of this loop. Essentially, the power source has a fixed amount of energy that it can distribute to the components of a loop. A loop is a closed path in an electrical circuit. This circuit has only one loop, shown in yellow, while the next circuit has two loops, shown in blue and red. Each loop is connected directly to the power source. Here is the formula for Kirchhoff's second law. In a loop, V at the power source is equal to V1 plus V2 plus V3, and so on, where V is the potential difference or voltage in volts. There is only one loop in a series circuit because there is only one path for the current to follow. The potential difference at the terminals of the power source is equal to the sum of the potential differences of the components in a series circuit. Kirchhoff's second law is used to calculate the value of the potential difference at the terminals of a component in an electrical circuit. In this example, the voltmeter measures 9.0 volts at the terminals of the power source. Bulbs 2 and 3 have a potential difference of 2.0 and 4.0 volts, respectively, at their terminals. What is the potential difference at the terminals of bulb 1? According to Kirchhoff's second law, V1 plus V2 plus V3 is equal to 9.0 volts, which is the potential difference at the terminals of the power source. The formula to find V1 is 9.0 minus 2.0 minus 4.0 volts, which equals 3.0 volts. The potential difference at the terminals of bulb 1 is 3.0 volts. In a parallel circuit, there are multiple loops since the current can take different paths. Each loop is connected directly to the power source. The potential difference at the terminals of the power source is identical to the potential difference at the terminals of each component in a parallel circuit. For example, in a parallel circuit with a potential difference of 5.0 volts at the terminals of the power source, each of the three bulbs also has a potential difference of 5.0 volts. In summary, the potential difference at the terminals of the power source in a series circuit is equal to the sum of the potential differences at the terminals of each component. The potential difference at the terminals of the power source in a parallel circuit is the same as the potential difference at the terminals of each component.